for the class. Okay, let me do it once again. Okay, so we are going to start our class today. Okay, so today we will look through the propagation and antenna. So again, this class we will talk about many physics, but conceptual level, no calculations involved. Okay, but make sure you know the materials in it. Okay. So before we do all the talk about all the stuffs, I would like to talk about what is the electromagnetic spectrum. So electromagnetic spectrum means the visible means all the light in our space. Okay, so we have got different kind of light, from extremely long radio waves to cosmic ray, which is gamma ray. Okay, all of them can be included in electromagnetic spectrum. Okay, yeah. And of course visible light is one of them. So for the radio, we will make use of the radio waves. Okay, so you can see I take this picture from the textbook. Okay, the beginners blah blah blah. Oh, did I give you the slides today? Just a minute. I seems I forgot to give you the slides of today. Here you go. Actually, this is the slide of last time, so you can just use the last time slide. I didn't make any changes. Because last time we have already do the hands-on. We didn't go through the materials here yet, so you can just use the same set of slides. It's okay. Just a minute. Okay, good. Okay, so for radio spectrum, we will make use of. You can see that here. We will make use of from we have set divide the radio frequency spectrum in like this. Okay, from very low frequency to extremely high frequency. Okay, just a minute. I'm going to. Thank you. Okay. Okay, so before we go through the wavelength, I'm going to talk about this first. Okay, usually we will draw a line at 3 megahertz. Okay, 3 megahertz. Why? Okay, so after 3 megahertz, it is ranging from high frequency to extremely high frequency. Okay, of course, below high frequency, they have got a new band called THF, but it will not be included in your textbook. Okay, so I have another slide later time, so you can take a look. I've actually got this one. Okay, so don't worry. I'm just going to have a very brief introduction first. Okay, normally we will draw a line at 3 megahertz. Okay, after 3 megahertz to gigahertz, it is high frequency, very high, ultra high, super high, extremely high. Okay, just the name. Okay, but for frequency lower than 3 megahertz, it is high frequency, medium frequency, low frequency, and very low frequency. So usually, you have to remember the names, but you can bear in mind that 3 megahertz is the line. Okay, after 3 megahertz, high frequency. Lower than 3 megahertz, medium frequency. Okay, I'll remember in this way. Okay. And you can see that in our electromagnetic spectrum, it includes a lot of stuff: radio waves, infrared, visible light, and gamma rays. Okay, all of them are called electromagnetic spectrum. But today we are just going to talk about this one. We are not going to talk about the visible light. So when we talk about light, we have to introduce what is frequency and wavelength. Okay, once again, last time we have talked about frequency and period, right? Do you still remember frequency and period? Frequency is 1/t. Okay, for wavelength, we'll introduce another new unit to you, which is wavelength. Okay, So when wavelength is defined as one complete cycle of the wave travel in free space. Okay, so we have to emphasize the term free space. Okay, free space in the space, not vacuum, but have nothing in it. Nothing in it. Okay, the most ideal case. So we will just give it a most ideal case and saying that, hey, we got nothing here. So even in vacuum, sometimes we have some ions or some other stuff in it, right? Or we say, hey, it is like quantum. We can get energy from nowhere. So we don't consider that. We will consider all things in free space, which means nothing. That most ideal case, okay? So sometimes you may see the textbook saying that's vacuum, that's really the old textbooks. So no, we don't use the term. We use free space. Or in Chinese we call 自由空間. Okay? So in the free space, I will just call it light, okay? The light means electromagnetic waves. So if you can say all the spectrum, all the frequencies in the spectrum, all of them are light, okay? Light travels in 3 times 10 to the power 8, okay? We got 8 0 behind, okay? So it is, you can count it yourself. I'm not sure what is argument. 3 times 10 to the power 8. Got 8 zeros behind, meters per second in free space, okay? So the wavelength can be defined as F equals to speed of light divided by wavelength. So you need this, you have to remember this formula, okay? Of course, hey, you may argue that light is 299 point something, right? No, we just make an approximation, saying that light, speed of light is 3 times 10 to the power 8. In your exam, you will meet questions like unit conversion, okay? Or sometimes they may trick you. They will ask you about the frequency and wavelength. Maybe they will ask you, hey, what is the wavelength unit conversion? Or they give you a calculation, and they may not give you frequency as a choice, okay? They may give you wavelength as a choice. So you have to always remember how to convert the units, okay? The formula is here. F equals to 3 times 10 to the power 8 over wavelength. Okay, wavelength in meters. Oh, actually it is wrong, okay? Hertz is here, okay? Hertz is here. It's not Hertz, okay? Hertz should be put here. So when you copy your notes, bear in mind that you don't copy it wrong. The Hertz should not be located here, okay? The Hertz is here. The textbook is wrong, okay? Okay, so yes, okay, yes. Let me check. Yes, okay. Okay, so we have got an example here. Find the wavelength of the light wave generated by amateur transmitter operating at 7.255 megahertz. Okay, so how are we going to calculate it? It's easy, right? Megahertz. So frequency is in megahertz, right? So we can put 7.255 megahertz here and set up an equation. Let me bring up my Excel. So the calculation will become, we got our frequency is 2. Oh, I put it twice. 7.255 mega. What is the does the mega represent? 10 times 10 to the power 6, right? Times 10 to the power 6. Okay. So we know the speed of light is 3 times 10 to the power 8 divided by the frequency. So the answer is 41 in meter. Okay, 41.35 in meter is the answer. Okay, let us check the answer. Yes. So you know how to do the unit conversion now, right? Oh, if you are not sure, I will just use the whiteboard. Okay, sounds good. Do I need to show my calculation once again? First, you find out what is the exact frequency. Mega, so this is 10 times power 6, 10 to the power 6. Okay, and you do set up the equation. Speed of light divided by the frequency, so it will become wavelength. Okay, so if they give you the wavelength, you can just do the same. Okay, I can just use this number like this one. Okay, I can just set up the equations. What is the frequency of 41 megahertz, 41 meter wave, which will be right divided by which will be 10 to the power 8 divided by this one. So you will get the frequency from wavelength. Okay, speed of light divides the wavelength will become frequency. Okay. So I didn't make a new equation for you. You can just swap the f and lambda. Okay, this is lambda. If you see the lambda, you will know it is wavelength in meter. Let me change the sign in real time. Hey. No. Let me do the slide in real time. Okay. So you know the trick, right? So lambda is in unit meter, and frequency is in unit hertz. Speed of light is meter per second. Okay, speed of light is meter per second. For this one, you have to memorize it. Okay, this is important to you. You will meet questions like this, or they may just give you, hey, they may give you some types of matching, saying that, hey, I'm now using UHF, so UHF should include what kind of frequency? They may ask you questions like this, okay? And you know how to do the frequency, okay? From very low frequency, it is 3 to 30 kHz. Low frequency, 30 to 300. Medium frequency, 300 to 3000. Or we say 3 megahertz. You can also use 3 megahertz to represent it. HF, 3 megahertz to 13 megahertz. VHF, okay, so we will say VHF and UHF are the most common frequency used in short distance. Okay, 30 to 300 megahertz. Like if we are using VHF, we normally use 144, which is the ham band, the band that is dedicated for hams. UHF, so you will see why we always use 400 something. Okay, and you can also see that actually our television is using UHF for transmission. Okay, Do you still remember which frequency is used for TV broadcast? No, I guess. It's actually 400 to 800. Okay. How about FM radio? Yeah, FM. Elephant is correct. How about FM? Actually, FM and AM is for some common broadcasting frequency, so you have to remember it. Why? Because in sometimes the questions may trick you, saying that can this frequency be used by the ham? Of course, from 88 to 108 megahertz. No, it is dedicated for FM broadcast. You can't use this band for sending signals. Okay. And AM. I will just leave the homework to you. What is the AM band? It actually around here. So you can have Google it. Okay. It should be about 1,000 something, 1,080 something kilohertz, as I remember. Yeah, 500 to 1,000. Just a minute. Let me bring up my cam. Okay. So that's why if you already have some image in your mind, you already know which frequency can be used by ham or frequency can't be used by ham, which helps you in deducing the answers if they ask you about law and regulations. Okay, so you can combine this image and the ham band, which is in NXB1, the allowed frequency. So do you still remember the primary bias and secondary bias, that kind of stuff? Yes, you have to combine this one and that one, two of them in your mind. Okay. Okay. SHF, EHF, and THF. Okay. I'll introduce this one because it appears in your exam, not because I want to, not because it is commonly used. Okay. For commonly used, VHF, UHF, HF, and MF. Okay. VLF and SHF, no, it is not that common anymore. But of course, hey, you may argue, super high frequency, my Wi-Fi lies here. Okay. You can argue that, but it's not that common in ham. Okay. Okay. So bear in mind, you can draw a line in the HF. Okay. After 3 megahertz, high frequency, very high, ultra, super, extremely high, tetrahertz, high frequency, THF. Okay. And below 3 megahertz, medium, low, and very low. Okay. So we are going to talk about the we are not going to talk about the modulation here, but I can give you some more deep down details. Okay. In the AM, oh, you guys will still listen to the radio, right? The FM radio. FM radio is lies here. It's high frequency. Okay, high frequency. No, not high frequency. Very high frequency. Very high frequency. So the broadcast cannot go very far away. Okay. So we will talk about it when we talk about the propagation. The propagation. The different frequency you use will decide how long you can transfer the signal to. Okay. It's highly related to the wavelength you use. Okay. And HF, we usually use this one for distance, DX, distance communication. For medium frequency in Hong Kong, we use it as AM broadcast. We use it for AM broadcast. Yes. So does it mean that we must use AM broadcast in medium frequency? No, it's not a must. Okay, it's two concepts. The wavelength and modulation are two concepts. But hey, there's someone also saying that I listen to the medium frequency radio, and they will represent it as AM. It's just because the common broadcast method for AM is using medium frequency. Okay, just because of that, not because of AM must use MF. Okay. And VHF and UHF, the common handheld radio, the frequency that is used for handheld radio. Okay. So you can remember this one. Okay. So I can give you some exercise now. Okay. I can give you maybe 2 minutes um, can you calculate, like I will give you ultra high frequency, right? What is the frequency in like 450 megahertz? What is the corresponding wavelength? Can you show me? I will give you a little exercise here. Maybe I type it in here. Okay. I will clear this one first. I don't know the answer actually. What? I'll just give you the what is the, maybe I give you another question. What is the frequency of 21 of okay, what is the frequency of the light with 21 meters wavelength? So can you calculate it for me? Why I use 21 is because it's a multiplier of 3, so you can calculate it very quickly. So at the meantime, I will grab a bottle of water, so you can try it first, and we will go through it later time. I didn't prepare the answer for this question. But 21 meter band is quite a characteristic band, because this wavelength is usually used for HF. I can give you a hint. It's usually used in HF. Okay, distance communication, HF, high frequency. So you can refer to here, HF. I have give you a hint already, saying that the band should lie here. How to calculate it? 21 meter band. Hey, what is the answer? Anyone want to try? Or I can give you some more times first. 40. Yeah, I guess it's around this here. So I can give you the hints. So we have C equals to yes, you have to know what is C. Usually for wave we just use V, but speed of light we will give them a character called C. So C is speed of light. Actually I don't know, so I will just do the calculation here. And wavelength is lambda, which is in like a Chinese character yap, okay? 21, right? So the frequency will be this one divided by this one. This is hertz. So just a minute. Let me. So you know the answer. It will be 14.29 megahertz. Okay. So sometimes they may give you this one. They may give you this one. It depends. It depends on the exams want to trick you or not. Okay. If they want to trick you, then they may give you this one, because this is not that familiar. It doesn't look that familiar to you. But if they give you this one, they're good to you, because you know mega, you can just do the conversion in hand. Okay. So the answer is 14.29. Okay. Or so you sometimes saying that, oh, hey, they will give you a round up. So I didn't include it in my slide, but sometimes they will, in practical world, they will say that, hey, I'm playing with 14 megahertz, for 50 megahertz, I'm playing 20 meter band, 10 meter band, that kind of stuff, 7 meter band, that kind of stuff. So you can, if you're familiar with that already, you don't have to do the calculation. But hey, if you really do the calculation, you will find like a little bit of calculation roundup error. Yeah, but in the ham world, they will just ignore the error. Yeah, but it is not important when you deal with the exam. It is a bit like a general rule in when you communicate with another ham. They will sometimes use frequency or sometimes use wavelength. Like in HF, sometimes they will just call, hey, I'm playing with 40 meter wave, okay, 40 meter wave. So in that sense, you have to do the conversion in your hand, okay. 40 meter band, I'm not sure how long it is, but you can do the calculation. So you see that I'm lazy. Just a minute. Okay. So this is I found this in Wiki. Okay, this is a very good illustration on the high frequency radio bands. I really want to find out. I actually find Wiki and see are there any low frequency ITU radio bands, but no, I only found the high frequency. So you can see that, hey, if I really want to memorize this one, HF, VHF, UHF, you can see this chart, a very good chart to me. If it gives you a very good illustration on the ITU band, the wavelength, the relationship between the band name, frequency, and wavelength, all in one. But it appears in high frequency. Yeah. So that's why I still put it here. So if you don't want to look at this chart, you can look at this one. They are equivalent, except not having the low frequency. Okay. The most important message I would like to bring out: if you find it very difficult to memorize the magic number 3. Okay, 3 megahertz to 30 megahertz, very high frequency, and the rest of them you can just fill in 0, right? You can just memorize by filling 0. Very high, ultra high, super high, extremely high. In the English, it is quite straightforward, but in Chinese you will find it is 高頻、超高頻、甚高頻、特高頻. So it is really hard to memorize, and you will find that the translation between China and Taiwan, they are not the same. They actually differs. But luckily, in your exam, even in Chinese exam, they will give you UHF, they will give you VHF, so you don't have to worry about it. Okay. Don't worry about the translation. Yeah. If it is in a very weird form, you can just ask for clarification, or they will already give you the terms or the English translation behind. Okay. But you are doing the English, right? So it is even more straightforward. You don't have to worry anything. How about high? So in reverse, high, medium, low, very low. That's straightforward. So if you really can't remember anything before the exam, just remember HF, and you can fill in the blanks and complete the rest of them. Okay? At least remember this one. At least remember this one. Okay? The high frequency. Okay? Hey, how come it is just slide 9? Oh, okay, so talk about wave propagation. Okay, wave propagation we use. Let's see. Okay. For the rate, so I'll just skip this one. Okay. The tools are basically the same, so I will use this one for explanation. For the light waves, we will have different kind of form of transmission. Okay, so you don't argue with me. Yes, the light is transferred in a straight line. Okay, of course you may say, hey, it bends over gravity. No, we don't consider that. Okay, light is transferred in a straight line. Okay, we ignore the extreme case. Okay, so we have different forms. If they pass through a material, they may have transmission, which is passing through the materials, but the signal, the light may, the signal strength drops. Okay. Reflection, like if they are shining through a metal surface, all the lights will be reflected. Okay. Refraction, if they pass through water or glasses through a medium, the light will bend a bit. The light will bend a bit, bend in the medium. Okay. So this is called refraction. Okay. Diffraction, which is if they pass through a hole, a very tiny hole, especially for low frequency. The lower the frequency, the diffraction is more can be found easily. Okay, appears more often. Okay. Absorption, if they pass through some materials, the signal may just disappear. Like it is like a bit of transmission. Okay. Scattering, a different form of reflection, but scattering will be discussed in our class. Okay. Yes, we call the propagation method called tropo scattering. So it is about scattering. Actually, it's just a kind of reflection, but it like the light is shining on a ball. Okay, so the angles will become different. This is a very flat surface, and the reflection, you can calculate the reflection angle. Okay, directly. Just one way. Okay, but scattering, the light may scatters around. The reflection angle appears differently on the surface. Okay. Yes. So now I will go through it one by one. But when you are studying at home, you don't want to go through this kind of words, very messy words. You can just refer to this diagram. Okay, and it will give you a very quick grasp of the knowledge. Okay, refraction. So radio waves, actually all kinds of waves will be reflected or bent. Actually, it is bent, but to look professional, we got the terms in physics called refract. Okay, not reflect, refract, which is bent. Okay, when they pass through a medium to another medium. So the word medium looks very professional again, right? So medium is just passing through different materials. Okay, passing through different materials or different stuffs. So in physics, it looks professional. We call it medium, or in Chinese they call 介质. Okay. If they have a different density, and when the light pass through the medium with a different density, the light wave will bend. Okay, like they will bend in water. So that's why when you see the fish in the swimming pool or on the beach, the fish actually locates a bit lower than you see. Okay. Still remember the high school the junior physics. This is still refraction. Okay. Yes, skywave propagation. We'll go through it later time. But hey, this is important. This is one method. If you okay, we've got 4 major propagation methods of radio waves, and one of them, especially the skywave propagation, makes use of the refraction. Okay. Diffraction. Okay. Diffraction in Chinese is called 辐射 or 顯射. Okay. But English they got one term, diffraction. Okay. So it is actually they pass. The light will just go in straight line. But if they go through some pointy stuffs or go through a hole, the light will become going in different directions. Okay. Radio will pass behind solid objects with sharper edge, like this one. The signal source. Okay. So actually this barrier will block all the signals, right? It should block all the signals. So no signals should go here, right? But the light will diffract over here. So that's why sometimes if you listen to some radio waves behind the mountain, the lower the frequency of the wave, you may have a bigger chance to listen to that radio. But if you are listening to FM, you may not be able to listen to the radio. Okay, this is the reason why. The diffraction angle is larger if they have used a lower frequency. Lower frequency, more diffraction. Okay. But just think it this way: if the light pass through a hole, they will go to different directions. Yeah, just like this diagram shows. I will draw it in the whiteboard. Hope you can see. Hey, how come they put this in water? Let me pull it out. Okay, I'll use it.我未入嚟，得，好啊，記得通知我，因為我真係會睇唔到啊。入咗嚟咯喎，有人 approve 咗，好嘢，感謝會長 approve 咗。I remember this one is not a good pen. I must use this one. Or we have a good pen here. Thank you. Okay. I will illustrate it this way. You see me? Okay. The lights actually, if they are traveling in the wave, if the wave is traveling in straight line, actually they will do it this way. Okay. The light wave. But if they pass through a hole, if they have a wave like this, they will bend in different angles. They will become larger waveform like this. Okay? So this is called diffraction. So normally, if there is a guy here, okay, see, if they have a guy here, they cannot see the signal. Like this is just think it as a laser. Okay, they cannot listen to the signal. But after diffraction, even they stand behind the hole, the diffraction they may have a chance to listen to receive the signal. Okay, this is called diffraction. It is important actually. Okay, so you. How come I have done? I forgot that I include the image here. Okay, so I'm going to talk about the aperture. Okay, just think it this way: if they have a hole, the light will bend. Simple as that. Okay. And yes, I'm not going to talk about the aperture, but you will see that larger wavelengths, higher level of diffraction. This will be important. Okay, this is important. Don't ask me why. Please, because the wave is how can I put it this way? It is the nature of light. I'm not sure why. Just remember that. Okay. So you see that compare these two diagrams. Okay, the aperture, which is the hole. They have the same size of hole, but the large wavelength, the higher level of diffraction, the light bends more. But lower wavelength, the light bend less. Just simple as that. Okay. Oh. Yeah. Have I? Oh, I just include these two. Okay. So I have just talked about the refraction and diffraction. Are there anyone want me to explain more on reflection and scattering? If not, then we'll just go to the propagation. Let me know in WhatsApp or in Teams. No, then I will just continue. Okay. Sounds good, right? Sounds good. Then I will talk about the 4 types of propagation. This will be important to you. They must ask you questions on this. Otherwise, they don't have questions asked you. So you must remember this 4. Okay. We have 4 different types of propagation. So in different textbooks, no, they will have different names. So you can, of course, you can refer to the syllabus in OFCA, but in practical, I will teach you all the names first. Okay. The first one is direct wave, and sky wave, ground wave, and trouble scatter. Okay, trouble scatter, tropospheric scatter, or in short, trouble scatter. Okay. The first one is the easiest to understand. Okay, the easiest to understand. Direct wave, which is, if you can see it, then you can transmit the signal. Line of sight, you can see it, then the signal can go here. Okay, so VHF and UHF, we got direct and refracted wave for them to propagate. Okay, the word propagation means transfer of signal. Okay, propagation means transfer of signal. Okay, so we will talk about a lot of propagation. You will always hear me use propagation, this word propagation, throughout this lesson. Okay. So, in simple, if the antenna can see the receiver, then yes, the signal can be transferred. But in reality, direct wave does not limit to seeing the antenna, the receiver. Okay. Sometimes the wave can have different paths, which is reflecting from the sea, reflecting from the earth. Okay. So you can think that sometimes the other objects can act as a mirror. Like the light, right? How can I talk about it? Yes, you can't see, like you are facing the mirror, right? So sometimes the light does not go directly to your eyes, but reflecting from the mirror. Okay, same as radio wave, but this time the reflection does not limit it to mirrors. Sometimes they use ground, they use water, they use different kind of medium as the reflection. Okay, but in short, they got all the things in common, or in in common. They all transfer in straight line. Okay, they all transfer in straight line, and within a short distance. Okay, actually it's not that short, but you can think it as a 50 kilometer as a line. Okay, as a barrier. Okay, they can just travel, compared to all the other methods. Line of sight have the covers the shorter distance. Okay, I will have a summary diagram to you, so you don't have to worry about it. Shortest. So you can bear in mind 50 kilohertz is the must. Okay, so it's like FM radio, right? You have even a kilowatt for transmission, but it can only cover the whole Hong Kong. Okay, out of Hong Kong you can't receive the signal. Simple as that. Good example, huh? VHF and UHF. Okay. Any more questions? This should be the easiest one. If you can see, so sometimes if you are in the surrounded by mountains, that's why we will need some what is the term 中繼? I forgot in English. Let me repeater. Yeah, repeater. Sometimes that's why we have the repeater to redeliver the signal. Yeah. Oh, let me sign in again. Okay. Just a minute. Hey. 放緊。If you can't get in, let me know again. I should already press the button and let you in. If you can't get in, let me know. Okay. Or I can just kick you off first, because I think I approved 3 times in a row, but I can't let you in. Oh yeah, they can't hear me. Poor you. Really, poor you. Deny first. Yeah. Yeah, rejoin, right. Good. Really good. Okay, let's continue. So, line of sight or direct wave, it is the simplest form of transmission. Okay. Okay. I don't want to bring up complex transmission method first, so we will just stick to direct wave, VHF, and UHF. Okay. Of course, in reality, it may differ. Okay. You can play with a lot of weird stuffs when you got the license. Okay. Ground wave. Okay. Ground wave is a special form of diffraction. Okay. So it will diffract along the surface of the Earth. Okay. Diffract along the surface of the Earth. Okay. Which no, you don't have to memorize the polarity. Okay. So the form of propagation travels along the surface of the ground or water, which is the surface of the Earth. Just think in this way. It is important at low and medium frequency. AM broadcast use ground wave propagation during daytime. Okay. In short, it's like this. Okay. We are not going to talk about the sky wave yet. We talk about the ground wave. Yes, this is the best image I can find in the web. Okay. So if you have the Earth, the ground wave. Let me. I found that I didn't have a very good illustration. Let me draw it. So I'll keep this one first. Okay, this is diffraction, right? So diffraction. Okay, I should put this one. So it is a special form of diffraction. Can you see the whiteboard? Let me make sure you guys can see my whiteboard. It should be clean. So, it's flipped. It's flipped. Don't think of this one. A. The camera app sucks. So if I minimize it, it will stop recording immediately. No good. Okay. Okay. So look at my screen. So if they have a diffraction like this one, actually we have talked about a hole, right? In our last case, we will introduce the wavelength will become this, right? So actually they got a special form of diffraction, which is this one. How about if I have a wave like this one, when they pass through this barrier, the wave will become this one. Okay? It will just bend on one side. I hope you can see the screen. So for ground wave, they use a very low frequency, which is low frequency. Diffraction will the level of diffraction will become very high. Okay, it diffracts a lot. Low frequency, diffraction. Low frequency, diffraction. So at the for low frequency, use MF, they have a characteristic of apparently low frequency compared with others. Okay, so that's why they have a very high level of diffraction if they mix this kind of stuff. Okay, so think in this way: the antenna is this way, the barrier, the whole Earth will act as a barrier. That's why when they have the signal emitted, they will bend along the Earth's surface. That's why the signal can go very long. It can go through a very long place. Of course, it is still shorter than the skywave, but for ground wave, it can already travel like 100 kilometers, much longer than VHF and UHF. Okay. Yes, this is a better illustration than my slide. Okay. Yes. So you see that it uses the curvature of Earth, bends the signal. Yes. And low frequency, level of diffraction is higher. That's why this is how the method they use. How they can utilize ground wave propagation. Okay. You don't have to go through all the details, but you have to memorize some characteristics. Yeah. So they may compare for VHF and UHF. Like if they VHF and UHF like here, they may not be able to communicate. Like if they do it this way, they transfer the signal in straight line. They can't. This is TX, which is the transmitter. This is ours. The TX is transferring the signal in straight line. The receiver cannot receive it because of the curvature of Earth. Yeah. One reason why VHF and UHF can go very long distance. So you can take a picture. Actually, this is quite good, the illustration. Okay. Yes, but still, because the Earth's surface will absorb a portion of energy, that's why the energy can't go to infinite distance. They will the signal will become very weak at the point. Yeah. They can't go through the globe. No, they can't do this. Okay. So you can see the ground wave. Yeah, they can of course travel a very long distance compared to VHF, but still, it is being affected. They can't go through the globe. Okay. The first two propagation method is still easy to understand. Skywave is the hardest part. Okay. Skywave is the hardest part. But hey, you may argue, oh, okay, give you a very brief understanding before we go to the details, okay? Remember this one? The diffraction, relation between diffraction and ground wave, okay? And low frequency. Then I will go to the skywave part. Don't worry about it. If you can't see the screen, actually my slide is good enough. But I would just want to give you a quick picture on that first, so you won't have a lot of questions in your mind before we talk about the details. Okay. Oh, I can't do it. Let me just give this. So the globe is here. Perfect. we got some, this we call troposphere, or we say it is the atmosphere, okay? The atmosphere is very thick, right? So think it this way, okay? The atmosphere, all of them are atmosphere, okay? When when the signal is here, we call TX, we call RX, okay? RX means receive, TX means transmit, okay? So when they give you the signal, I'll just do dotted line, okay? I'll just do a straight line. They may reflect, okay? This is refraction actually. In your textbook, it is refraction. Not reflection, not 反射, it's 折射, okay? So if you read, they really ask you about the transmission for skywave, you will have to remember this one, okay? Reflection. If they tell you saying that you're wrong, you can give them a textbook, their reference book, and tell them they are wrong, okay? Reflection. They got different little ions here, so the signal will collide with, will refract through the ions and transmit the signal back to the earth, okay? it's my mistake. This is how you can receive. They will make use of the simple as that. This is the general picture of skywave. Okay, and we will go through it one by one. Okay. So we're going to introduce two methods of propagation using the atmosphere. The one is skywave, another is tropospheric scatter. So we'll go through skywave first. Skywave, blah 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 blah, and bang to the ionosphere, blah 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 blah. Very long words, right? So just listen to me. You don't want to go through all the words. In the atmosphere, there is a layer called ionosphere. Ionosphere. Okay. In Chinese, it's called 电离层, ionosphere. So in ionosphere, it's very good for radio propagation. So you see that it's the atomic blah 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 blah. So they caught a lot of ions here. You can think this way. A very low pressure and importance blah 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 blah. Okay. Just remember that ionosphere, because it has very a lot of ions here, which helps for the skywave, for the radio wave to transmit, okay, or propagate. So the next sentence is the very important, helps you to understand why it is called ionosphere. The higher energy UV light and X-ray help ionize all these molecules. Okay. That's why they have a broad region where ions are created in relative abundance. That's why it's called ionosphere, because they have a lot of ions. Simple as that. Okay. Of course, in your exam, it's not that simple. I'll give you the general picture. Atmosphere, they call a layer called ionosphere, which got a lot of UV. Okay. Another point is ionosphere is not as an exact. If you divide the atmosphere in this way, like troposphere about the temperature, you have troposphere, stratosphere, mesosphere, right? Temposphere. But we are not. The definition of ionosphere does not lie on the temperature or the kilometers. It's about the area where they have an abundance level of ions. Okay, so it lies around mesosphere and thermosphere, 50 km to 600 km, around this level. Okay, so hey, if they argue with you, oh, does ionosphere equals to thermosphere? No, it's not an equal sign. Okay. After introducing the ionosphere, we have to also talk about the regions. For the ionosphere, they got different layers called D layer, E layer, F1 and F2 layer. Okay, they got 4 layers. You have to remember it. And because, as we just mentioned it, the ionosphere is because of the abundance of ion, right? It's about the UV and X-ray, right? So the ionosphere will change by sunlight and seasons. Okay, like in winter, it will have at daytime and nighttime, they already are different. Okay, for daytime, okay, you see that for side A here, it is the daytime. So you see that, hey, they got D, E, F1 and F2 layer. But in nighttime, because they don't have sunlight, they can't produce a lot of ions. So they got only E layer and F layer left. Okay, E layer and F layer left. But most of the time when we do distance travel, distance communication, we prefer at nighttime. Yeah, I'll talk about it later time. Because the D layer will absorb most of the radio wave, and it is not good for distance communication. That's why we will prefer to do the communication at the evening, like around 6 o'clock. Okay, this is the best time for HF communication or skywave communication. Okay, yes, I should put it in skywave. We make use of the ionosphere, where the time D layer is a bit weak, and we have the abundance level of ions, which helps for the signal transfer. Okay, signal propagation. And because of we can't look at the weather. The weather won't affect the ionosphere. Okay, it won't affect. Only the season, the temperature, and solar effect will affect the ionosphere. Why? It's because, still remember that the high energy solar, EUV and X-ray radiation will alter the ionosphere. So that's why it is highly related to the effect of sunlight. Yeah, that's why solar cycle and daytime, nighttime, and the season, it will change. Okay, so at the winter time, you can always think that they will have a weaker ionosphere and ionosphere. So they will just have layer E and layer F left. Yeah, in winter, you can think in this way. Simple illustration from Wiki. At nighttime, they will have just E and F left, and for daytime, they have D, E, F1, F2. Okay, so you think this way: F layer migrates at nighttime, and D and E layer migrates at nighttime. Okay, it's better for you to also remember the distance between the different layers and the Earth's surface. Okay, I'm not sure if they will ask you or not, but if you remember that, it will help. Or think it this way: just remember the highest and lowest, so you can deduce all of them, right? Yeah. Good enough. This is all the explanations why at the daytime they got why the radio wave is absorbed by D layer, and why the E layer and F1, F2 layer is the best for skywave propagation. So if you want to dig through the details, you can have a look at that. But I think it is a bit over for your exam. Okay. This one is enough. Okay. Let me see which slides have we left. How come? We will take a break when we go through all the propagation methods. Okay. Let me go back to the D and E layer. Because D and E layer, they got a lot of things they can ask you, like the what are the factors that affects the ionosphere, the distance between the ground surface and different layers, why the daytime is not good for HF, skywave propagation. All these questions they can ask about you, just because of skywave is really, really special. Okay. We have just introduced to you D, E, F1 and F2, 4 layers, right? And sometimes when the temperature or the weather is good enough, or they can report that when they, after the rain, when the E layer is very abundant, they will call a sporadic E, okay? This sporadic E propagation, which helps elongate the travel distance. So the travel distance of the skywave propagation can go very, very long. Okay. Sporadic E. Sometimes they, in some very weird case, they can use VHF and sporadic E to do long distance communication. Like they can, after the rain, there are some Japanese guy can use handheld radio to call to Taiwan. It is possible, in theory and practical. It is possible, and someone has tried already. It's because of the, or we can say special E layer. In the notation, we can call it ES. Okay. So this is one extra information that you should know. Okay. Just think in this way. They got a very a cloud of iron. Okay. A cloud of iron. So that's why they can help to, just like let me think in this way. Just like a glass tube, 光纖. What is the English of 光纖? Let me think. I forgot. How come? Let me check. What is the English of 光纖? Hey, how come?
Fiber optics.
Yeah, fiber optics. Optics, yes. Light optics, okay. It's about light optics. Like they will do total internal reflection, that kind of stuff. You can think it this way. That's why, just like they give you a media light optics and let you guide through the radio waves to a very long distance. This is how sporadic E works. Okay? Just like light optics. Okay? They may not ask you, but in some notations, when you read the textbooks, they will teach you layer D, layer E, layer F1 and F2. But sometimes they will also tell you about layer ES. And now you should remember what is ES. Okay? A special E layer that can help extend the radio wave transfer to a long distance. This is how sporadic E works. Okay? Simple as that. You don't have to memorize a lot of stuff. Okay, so we have talked about a lot of atmosphere and what is the distance of different layers. So now we come to how ionosphere refraction works, which is a skywave, how skywave works. Okay, so the skywave actually in this way. Okay, they have a signal here, they send a signal up, and they refract along the ionosphere and go back to the Earth. Okay, this diagram. Okay, just like this diagram. So okay, and which looks very like reflection. So you see they got virtual angle, blah blah blah, right? It looks like it looks alike to reflection, but no, it in the nature is refraction. Yeah, this kind of reflection-like transfer is we call skywave propagation. Okay, just like a mirror, the ionosphere works like a mirror. Okay. Okay, quite important, quite important. All the terms are included in your syllabus. That's why I have to go through it. Yes. Critical frequency. The highest frequency that echoes from E and F region at the vertical incident. Zero angle, okay? Zero angle. It is called critical frequency. Okay? The higher the ionization of the particular attitude, the higher becomes the critical frequency. Okay, so you know that the critical frequency is in Chinese is called 臨界點，臨界頻率。Okay, so they will try to emit a signal perpendicular to the Earth. Okay, vertically. Why? It's because if the light wave, the refraction, the level of refraction will become very low if they do a vertical emission. Okay, you can think it this way. Yeah, they don't do a lot of reflection. Okay, they don't do a lot of refraction when they have a zero angle. That's why if they can calculate they can measure the critical frequency at that day, they know that all the frequency below the critical angle can be used safely. They won't escape from the Earth. Okay, they won't escape from the Earth. Okay, one more important stuff is the frequency a bit higher than the critical frequency, and if they are not emitting at 0 degree, it can be used. Think it this way: if they have an antenna doing in this way, of course they got a very limited space for you to reflect, right? But if they do it in this way, they got a light signal, they got a higher level of diffraction. That's why you can have a lot a wider range of frequency can be used, or even higher than the critical frequency. The critical frequency is just to measure at 0 degree. Okay? It's just definition. Okay? Every frequency below critical frequency can be used safely, and you can guarantee a refraction from ionosphere. Okay? This is the definition of critical frequency, because the ionosphere is changing at any time, so the critical frequency is not a fixed value. It can give you a range, or you have to do the testing before you can do the testing before you do the signal emission. Yeah, but of course you have a safe range that they can be used, guaranteed. Okay, just if you want to try some very weird stuff, you want to test the angle of it, you have to measure the critical frequency yourself. Okay. And maximum usable frequency. So the frequency vertical above critical frequency, the ionosphere will just escape to the ground. So this one, they will just go to the space if they below the critical frequency. Okay, but the highest frequency supported between those two stations is we call it maximum usable frequency. Okay, sometimes because like this one, you are not emitting at 90 degrees. You are not emitting vertically. You are emitting through an angle. Okay, so if you are emitting through an angle, the frequency changes. This time, the frequency measured that will be reflected to the Earth is called MUF. Okay, it is not critical frequency anymore. This is we call critical frequency. Okay, just 2 terms for you. So that's why they have a they have some reference for you. They call the M factor, but it is just for your reference. You don't have to memorize it. The maximum frequency, maximum critical frequency, and maximum is also the usable frequency. The maximum usable frequency, they are not the same. Okay, they have an M factor. But hey, you don't have to memorize this one. Just remember critical frequency and MUF. They are 2 different things, 2 different measurements. Although both of them are measuring which frequency can be used, they are not the same. Okay? Because of the angle of emission. Okay? So you can see that the highest frequency. So you can see that F1 can be used, right? F2 can be used. Lowest frequency. There are some. If your frequency is very, very low, they may be affected by any other stuffs. Like they cannot be absorbed or cannot be refracted by the ionosphere. Okay, that's why they have a range for you to use. Okay, just because of that. Skip zone and skip distance. Important to you. Let me just clear out all the stuff. Because sometimes I guess, why today I'm not using iPad? Because I forgot to bring my iPad. I'm so sorry about this. So I have to use the white. Because this part, it involves a lot of drawing, and drawing will help you to understand. That's why I have to draw it out. Okay. And ionosphere, I've talked about this, right? What is skip distance? Okay. So the Earth looks like this, right? You got an antenna here, right? So let me just draw the ionosphere as a single line. Okay. Here's Earth surface. Okay. When the signal emits like this one, they will reflect to the Earth, right? As I've just mentioned in the direct wave, sometimes we have different reflected wave. So in the ground, it will jump to the ionosphere once again and propagate down. Okay, this is why we call they have different hops. Hops. This keyword hops. This is the word telling that the wave refracted from the ionosphere reaching the Earth, reaching the ground surface, they will be reflected to the ionosphere once again. This is called hops. So you may hit, hey, it is 1 hop, 2 hop, okay? And sometimes the signal landed here, they can cover this range, okay? This can be received. This range can be received, okay? Okay. So this zone, we will call it as skip distance or skip zone. The zone that cannot receive any signal. Okay? Because the skywave propagation makes use of the refraction from ionosphere. The location the signal lands cannot be controlled. Oh, no, I should put it this way. If you are emitting a signal with an angle, of course they will land it to a very far distance, and only this place can receive your signal. That's why between the antenna and here, where the signal lands, they can't receive any signal. This is we call the skip zone or skip distance. The zone is just an area, and the skip distance is the measure between the closest place where they can receive the signal to the emission antenna. Okay. That's why you can see that, hey, the signal, we can receive a signal here, right? So that's why we call this one the skip distance, which is equivalent, right? You see that this diagram and the one in the whiteboard, they are equivalent. And this one is much better again, okay? And you see that this signal have multiple hops, right? Multiple hops. So explaining that the skywave propagation, sometimes when the signal hits the ground, they will reflect it, go to the ionosphere once again, and have the skywave propagation. Okay. So, but the signal becomes weaker and weaker. Eventually, they will die out. Okay. Sometimes you can see some book saying that it is skip song, skip distance, or dead song. Dead song. Yes, 直正確 dead song. Okay. But they are equivalent. Okay. So, one more extra thing to talk about. So we cut an emission angle, right? It is theta, right? So how about if we have an emission angle at very, very close to 0 degree? I emit here the ionosphere, right? It is right. I have the signal very emitting. Actually, the measurement is not like this. The measurement is from here. I'm not sure. The measurement is here. Okay. How about if the emission is very close to the theta is very close to 0. Then when they reflect the signal back, I'll just create a reflection. Okay. You see that the skip distance become much smaller. Okay. So that's why the skip zone and skip distance, it really depends on the angle you emit the signal. Okay. If you do it at 0 degree, of course, you don't have skip distance. You don't have multiple hops. All the signals will reflect from here to here, right? Like this one. The signals will reflect from here to here. You won't have any other place to be able to receive the signal. But if by changing the theta here, just like the mirrors with lasers, you have to play around. So you can see that the skip distance can be altered. Okay? It's not always a fixed value. So sometimes it really depends how you want to utilize the HF. You can play around with it like this. But it is not that important, so I didn't include it in the slides. But because this is one of my questions when I attend the lesson, that's why I can explain it to you now. Sometimes, yeah, I think for a whole week, can I change the skip distance? Is it a fixed value? No. It really depends how you emit the signal. But there is one more, always a but. The HF signal, the HF antenna, sometimes is very large, and you can't change the angle of emission easily. So that's why sometimes they will just treat it as a fixed value. But of course, if you want to, you can always change the angle. Yeah. It just depends on how much effort you have to put in. Okay. Very close to the. 咦？呢啲咪㗎？出事啊！就係咁嚟㗎。Ionospheric fading. Okay. Ionospheric fading is because of we have talked about it. The ionosphere, the level of abundance is not a fixed value. So sometimes when the UV changes, they have a drop in ions level. The ionosphere cannot be helped emitting signals, transmitting the signals anymore. It is because fading. Okay. At some point, the abundance of ions become less dense, and at some point it's much denser. So when we are saying that the radio signal you citizen will become far long distance, it become weaker and stronger. It alters a bit. So it is called ionospheric fading, which is QSB. QSB, okay? Oh, QSB. You can check the Q code. There is a Q code especially designed for fading. Okay. Yes. The fading is notable at sunrise and sunsets, especially near the MUF. Okay, but it's about the abundance of ions. Yes, and sometimes there is UV change. It will have fading, and if fading really occurs, we will stop the communications as fast as possible, because we know that the ionosphere is no longer can no longer transfer more signals, and the signals become very unstable. Yeah, this is because ionospheric fading. Yes, we have talked about it. How will the ionosphere being changed? Sunlight, level of sunlight, which is daytime, nighttime, and season, quite season, and the solar cycle. Okay. So the activities of the sun will have a cycle of 11 years. Okay. So that's why when at the 11-year cycle arrives, the activity of the sun become much stronger. It will emit more UV. That's why it will have more ions, and likely that the skywave propagation will be better at the time. Okay. And how do you know that this 11-year cycle solar cycle appears? You can when it reaches the cycle, the number of flares and sunspots will have more. They will have more sunspots and flares. In Chinese, 耀斑 and 太陽黑子. Okay. So you can see that the activities of the sun is much more vigorous. Okay. Everything is much more vigorous, having a 11-year cycle, and it affects the ionosphere, and it will help the skywave propagation. That's all. 3 elements of affecting the sunlight skywave propagation: level of sunlight, daytime, nighttime, season, and activity of the sun. Okay. The last one, tropospheric scatter. At the time when I studied the lesson, they didn't talk a lot about the tropospheric scatter, and I can't find a lot of information. But you can see this one, right? They got a troposphere here, right? In the troposphere, they got a lot of water molecules and dust in it. Okay, that's why it can help to when the radio wave shines on it, it will help scattered. When the light shines on small objects, it will scatter, and it helps for the tropospheric scattering. Okay, that's why we can use it as a long distance, a bit longer than the ground wave, and much more stable than skywave. Because skywave, I can't control the ionosphere, right? So that's why I make use of the troposphere. Of course, it have a very high energy loss. I have to use a lot of energy to emit the signal to compensate it. But it is much more stable compared to skywave. Okay. This is a summary. I found this graph is really good. It summarizes all the where ground wave will use low frequency, very low frequency, skywave, MF, HF, tropo scatter, VHF, UHF, and line of sight. Of course, in general, we usually use line of sight in VHF and UHF, but hey, line of sight can be used in many frequencies. But you don't have to bother this, okay? You can just memorize VHF and UHF is line of sight. Okay. Yeah, this is a really good summary for the propagation. Ground wave, it travels around the contour of the Earth. Skywave, bouncing between the surface of Earth and ionosphere. Troposcatter use the tropospheric layer to scatter the signal. That's why some signals will not be going back to the receiver. It will scatter around. It will scatter around really. That huge energy loss. Okay. Line of sight. If you can see the antenna, you can transmit the signal. Simple as that. Okay. So we can take a break now. So at last, when I studied my class, I just memorized this one with the DE F1 F2 level. Simple as that. I've talked about a lot of details in it, but if once you understand this diagram, you can have much less things to memorize. Yeah. Just 4 types of propagation. Okay, so we will now talk about the antennas. So you see that we have 2 different words here, antennas and aerials, right? In your in the OFCA documents, you will see that they will use the words aerials, but aerials is just the British form of antenna. Okay, the words are equivalent. Yeah. That's why when you read your Annex A and Annex B1, you seldom see the word antenna, but you will see a lot of words in aerial, even in your syllabus. Okay? Yeah, but the words are equivalent. It tricks me a lot. I always read the words antenna, but when I read through the documents from OFCA, I didn't find it, and I'm very afraid of it. Why? How come? And I do a lot of Google. First of all, we will talk about, we will divide antenna into 2 sections. One is omnidirection antenna and directional antenna. Okay. For omni or om, I don't know how to pronounce it. Omni, right? Omnidirection antenna. Okay. So the radio wave spread out equally as an increasing sphere. Okay. Which, in other words, they emit a signal in all directions. They will not have a direction. The signal is much stronger. No, all the waves they are the same. Okay. So first of all, I will talk about the isotropic antenna. Still remember the word dBi? Okay, decibel. We talk about decibel, dB, right? And in dB, we sometimes will refer it as dBd, right? Which is dipole antenna. And dBi, which is this antenna, isotropic antenna. Okay. So that's why they have different names, dBd and dBi. So now we are talking about dBi. Okay. Still remember that 0 dBd equals to how many dBi? Still remember that? 2.15. It is a bit important. Of course it isn't asked in my exam, but I think this should be memorized. This is from pure calculation. And if you want to buy the antennas from different stores, and you see that, hey, the antenna have 0.15 dBi gain, it's no gain. Cos 0 dBd equals to 2.15 dBi. Why? It's because usually we measure the antenna using dipole antenna, not isotropic antenna. Isotropic antenna, so we'll go back to what is isotropic antenna. Isotropic antenna is a theoretical antenna and which radiates equally in all directions, horizontally and vertically. Okay, the antenna have 0 dBd gain. This dB is dBd. Okay. Oh, I'm sorry. This antenna has 0 dBi gain, 0 dBi gain in spherical space, and have an efficiency of 100%. Okay, so you have different dB. You will meet this dB words many times. So isotropic antenna is like a sphere, and we will reference other antennas with it using the terms dBi. Okay, but it's not important. I just want to recall your memory the word dBi once again, and talk about what is dBi and why we have this weird term. Okay. No, this slide is wrong. This slide is wrong. It should be located here. Okay. Yes. So the second one is the halfway duplex or dipole antenna. Halfway duplex. 咩偶波咩？forgot. In Chinese is 偶極指天線. Okay. Dipole antenna. Okay. So it have characteristics of 73 ohms. Okay. No, it's different definition. We can't do anything else. So you have to remember that for a dipole antenna, it is 73 ohms, and it have a length of 1/2. Do you still remember what is lambda?
Wavelength.
Yes, wavelength. That's why we also call it half wavelength antenna. Okay. So you can imagine that if we want to do an HF communications, like 40 meter wavelength, 40 wavelength, then you have an antenna of 20 meters, which is a very huge antenna. You can think in this way. That's why in our development, that's why we have a very huge antenna at the back. One of the reasons why. Okay, this is how the dipole antenna works. Okay, will they ask you in the exam? No, I don't think so. Yeah, just a gist for you to understand when. Oh, there is one more stuff I have to introduce to you, which is the polarity. Polarity. Okay, this is propagation in horizontal. That's why we have to put the antenna in this way to receive the signal. If the signal is propagated in horizontal, then the dipole antenna cannot receive the signal anymore. Which is this is horizontal, right? If it's vertical, the E is vertical, then dipole antenna cannot be received. We can't receive the signal this way.
So right now it's sending and receiving.
It is just receiving.
Just receiving?
Yes, it is saying that the voltage changes in the dipole antenna. Okay, the voltage
How
changes.
the arrow is going that way and then this way?
Because it's just
AC.
AC. Yes, because the signal is just it's a high frequency alternating current. Okay, it's just like an AC signal. Okay, that's why when the signal passes through, it is a very high frequency alternating pattern. The voltage in this antenna will change in a very high frequency. Okay. Okay. And this is just an illustration how the antenna receives the signal, but not emitting time. How it's receiving the signal. Because the voltage change will drive this R, right? And this R represents the whole circuit at the back, receiving a signal. Okay? This part. The R represents this part. Okay? And the radiation pattern of dipole antenna is just a donut shape. It's no longer an sphere, it's a donut. Okay? It's commonly seen in measurements. Okay? So if you see a donut shape, you know, oh, it is an omnidirection antenna. Okay? But no, it is not necessary in this way, and it is just a theoretical case. If the antenna doesn't match with the frequency, then the wave may change, the radiation pattern can change a bit. But I'm not going to talk about it. I will just give you an image of omnidirection, dipole antenna, radiation pattern, like a donut. Okay. Polarization. Okay. So we will talk about. You see a lot of words here, right? I'm not going to go through these words. I will just go through this one. Okay. So if the voltage input, you see that's the polarization and the antenna, they have to match each other. Okay. If you emit the signal horizontally on a flat surface like this, the receiving antenna have to put in also horizontally to receive the maximum signal. Okay. If you have a vertical polarization, but your receiving antenna is putting in the horizontal, then we call this as cross polarization. Cross polarization, and your received voltage will be minimized, close to zero. And circle polarization, we are not going to go through it. I'll just put it here. Okay, and I'll explain it to you later time. Cross polarization is the most common polarization being used now, because it can compress the size of an antenna, but it will change to left or right, clockwise or anti-clockwise. But we are not going to too deep in it. We just let you know we have different polarization methods, and sometimes horizontal polarization is the best for signal transmission, but we may not use it every time. Like for TV signal, they already use the horizontal polarization, and we don't want to do any interference with that. Then we will use the vertical polarization to ensure there's no interference with the TV. Okay? So it's just case by case. Horizontal the best, but we may not use the best polarization every time. This polarization method may be occupied by others, so we will choose another method. Okay? So, but you know that if the receiving and transmission antenna does not match, the received signal will become weaker and weaker. Okay. And why I have to include circular polarization here? Because circular polarization is commonly used. How common? You see that all the antennas is straight line, right? How come I say that circular polarization is common? Like if you are doing some drones, controlling drones, especially first-person view, VHF, first-person view drone, you will see that the antennas at their goggles are using circular polarization, which become a very short antenna, but can deliver a very strong signal or receive a very strong signal. But at that time, you will have to bear in mind it is clockwise or anti-clockwise. Okay, so that's why the world changes. They got different polarization methods now. Okay. So no, it's actually 73, but I guess it's at range, so they won't trick you in this way. The halfway dipole is 73 ohm, but the textbook sometimes say it's 72, so it's like a round of error. But don't they won't trick you in this way. Okay, it's approximation. Okay, so if they want to make, they can make a full dipole in this way, and the full dipole will have a 300 ohms characteristics impedance. Okay, 300 ohms. They just fold it in like 4:1 impedance transformer. Blah blah blah. Okay, and the full dipole will have a very important characteristics, which is they will deliver a balanced signal. Okay, but hey, never mind. It is just an improved version of full dipole. Full dipole 73 or 72, and it will turn into 300. Okay, Simple as that. It's become a loop. It becomes a loop. Okay. Vertical antenna. Vertical antenna, they will have by the time when I study my notes, I found it is not writing in a very good. They don't have a very good illustration, so I can't understand it. Say that, hey, they use the Earth as another part of the dipole. So when I look at the textbook, I finally realized how they make use of it. They will use the ground, and they will stick to the ground surface, and the rest of the parts they will use the ground for the rest of the antenna. Okay, that's why you just use the very short vertical antenna, and you can receive signals, especially in handheld. They use the ground to act as a virtual antenna. Okay, that's why you can have a very short wavelength, 1/4 lambda long. Yes, and the ground will create the missing half antenna. Okay, commonly used, especially in handheld. Yeah, or you want to do some vertical transmission, then you don't have to do the dipole. You don't have to do the dipole. You just need 1/4 wavelength, the half of the dipole. Okay, vertical antenna. And this is the illustration of it. Okay, this is the ground. So you can omit the ground if you are sticking it on the ground or using some. Still remember when we talk about safety, we have different groundings, right? When the antenna is sticking to the groundings, so you don't need this kind of other antenna. You can just keep this part. Okay. This part is called the ground plane. This is the ground plane, have the grounding. Okay. Okay. So we have talked about virtual ground plane antenna, or we summarize it as vertical antenna, full dipole antenna, and dipole antenna. 3 different kind of antenna, which can commonly use to receive signal. Okay. So I didn't include it in my slides, but sometimes for the TV, we use V dipole, which is the dipole antenna become the V shape, or NTV. No, we are not going to dig too deep in it. Okay. Yagi antenna. So still remember when we go outside and have a look at our antenna, it is the Yagi antenna, or we say Yagi Uda antenna. It's because of 2 Japanese guys developed this antenna. So this is still commonly used. Very good. And if you have a chance to look at all the ceilings in Mongkok, and you will find that all of them are the Yagi antenna, just to receive the TV signals. Okay, and this is the first directional antenna and the only directional antenna that we will go through. Okay, directional. What does it mean by directional? You will see this one. Still remember the donut shape that we have shown in the omnidirectional antenna? The Yagi antenna will have an X shape, like an X shape. One side is stronger, one side is weaker. Never mind. We'll just put it on the. Never mind. I can find a space here. First, for the antenna, dipole antenna, it is like a donut shape when we do the front view, right? This is an antenna. For the antenna, we can change it this way. This is the ANT, and this is the radiation pattern. For the Yagi antenna, it is no longer an X shape. It is like this one. Okay. Directional. Okay. When the antenna is pointed this way, it should look like this. The Yagi antenna should look like this. But on directional antenna, it will have a donut shape like this. Yagi antenna from a donut shape to a one circle larger, one circle smaller, which is the same as this one. Okay, the radiation pattern. Okay, so what I have to talk about the radiation pattern. Still remember the negative 3 dB points. The radiation pattern is just an illustration of the negative 3 dB, minus 3 dB points, where the power is halved. Okay. Let me see how many slides have I left. No, I'll just talk to up to here, okay? Slide 58. Okay? Because I find that you guys are somehow yawning already. Okay, so this is the only directional antenna that we will go through. Okay? And the Yagi antenna, one note is called one element. Okay? So normally we will have 3 elements or 4 elements antenna. At least 3, okay? We have a reflector at the back, driver element, and directors. Okay? The driver and element here is we have 2 choices. Usually a dipole antenna or a fold dipole. Okay, dipole or fold dipole. You can think it this way: just a normal antenna, and we got metal strips put on it. You see this one is just metal strips, nothing else. Only 點解嘅？傻咗突然之間。Is the hey? Let me check the sky the teams. Is the teams is still here? Oh no! How come my camera is not working? Just a minute.應該蒙咗嘅，唔理啊。應該係我唔係，我 highlight 咗佢。Never mind. Oh, it may be the USB. The USB is broken. I found that my computer hangs. Okay, so even the God asked me to finish it very quickly. I will finish it in very quickly. Okay, the driver element, directors, and reflector. Okay, so the driver element is the only part that will connect to the transmission line, coaxial cable. The other parts are not connected. They are just metal pieces and metal strips. But after some calculations, they will find that the wave will reflect from the back. And this is some guides to help to make this wave narrower and narrower, more pointy and pointy. This is from the calculation, okay? Driver element. No. The only thing you will have noticed is the driver element is the only element will connect to the feed line. Okay. Oh, I have to also talk about what is how many elements of Yagi antenna. So you see that this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 metal strips, right? So we call it as 13 element Yagi antenna. Okay? So it's just you just have to count how many reflector plus driver plus directors, okay? And driver antennas okay. Never mind. You just have to remember the driver element is connected to the feed line. And we've got reflector, dipole, and or fold dipole directors. This we call the free Yagi antenna, the simplest form of Yagi antenna. Of course, you may see that hey, the reflector is a bit longer. So you may see the element to element is it's one. They got a very specific calculation here. The space between each element, you have to calculate it. Okay, it is not a fixed value. Yeah, of course, online they can help you to do the calculation. And reflector is longer than the dipole and longer than the director, a bit. Okay, so this is a bit longer than the half wavelength. So you see that it is a back loop, Of course, the back it can receive a bit of signal, but when you transmit the signal, you know that you should always use the direction of the director to point to the target you want to communicate. That's why sometimes we can hear someone is speaking, but we can't hear the opposing side when we try to. Oh, still remember last time when we listened to the Indonesian communications, we can only hear one of the radio, but we can't hear the opposite side because the opposite side is not pointing the antenna to us. That's why we can't hear. They are using a directional antenna. Yeah. Multi-band antenna. Why we have to talk about the multi-band is because sometimes they are saving up materials. They will use the same antenna with different band stop filter to make the antenna can receive different signals. Okay, so this is, still remember, this is the LC parallel circuit, which helps to limit the signal. Okay, which helps to limit the signal, prevent this signal. Oh yeah, if this part, it is like 40 meter operation, right? If this part is receiving the 10 meter band like harmonics stuffs, this band stopper can help to limit the signal. The LC circuit. Still remembered the resonance. So this is how the multi-band antenna works. They got different band trap here. Yeah. So you see there is 2 band trap, then you can have 3 different range to receive. Simple as that. So for dipole, you can still do the same thing. You have a band stop filter here, or we say band trap here. Okay. So that's for today. We will stop now. For the rest of the transmission cables, coaxial cables, we will leave to the next lesson. Okay. So see you next Tuesday. So if you have a chance to come back, please come back and take your